The discovery of the 113th element, nihonium, was one of the highlights of nuclear physics research at RIKEN in recent years. Dr. Hiroyoshi Sakurai, Director of RIKEN Nishina Center for Accelerator-Based Science, will now talk about the birthplace of such elements, the radioactive isotope beam factory. Dr. Sakurai, please.
Thank you very much for introduction, Ichioka-san. So I'm very happy to introduce our facility and also our research activity at Radioactive Iso Beam factory. Okay, so let me try to move. Oh, wow, fantastic. So I'm now changing the slide with my smartphone. Anyway, so first of all, let me introduce our science, technology, and innovation at RIBF. So scientific-wise, so we like to know how the elements are created in the universe. And we like to make super heavy elements as many as possible. And we like to, have a solution for the radioactive nuclear waste problem for that sustainable society. And technology-wise, we have heavy ion accelerators, and also that we have a nice technique to isotope separations. And innovation-wise, we have applications program for social benefits. And one is to produce alpha emitter radioactive isotope for medical use. And second one is heavy ion breedings. You can see that the bottle of sake, yeah, you can see, and that sake is special, made by the mutant yeast. So that sake is like water, very dangerous. Don't drink too much. But when you have a chance to come to RIKEN, please enjoy that sake made by mutant yeast. And the third one is electronics test for the space applications. So from now on, let me focus on the pure scientific program. Okay. Okay. So this slide shows that our facility, yes, and our facility is divided in two parts. So left-hand side, that is an old facility, started 1986, and the right-hand side is a new facility. So we are, our pure science is nuclear physics. So maybe everybody knows that how nucleus is made. So nucleus is made of protons and the neutrons, okay? So all the facility, at the old facility, we are focusing on the to produce the super heavy elements to move the high Z. Z means that the number of protons. Okay, so we are going to the high Z side of nuclear chart, and at the new facility, we like to go to the neutron-rich side. So high N, N is a number of neutrons. Okay, so so we have two directions. Okay, at the older facility, high Z, and the new facility, high N. Okay, so let me introduce the older facility a bit detailed. Okay, so this older facility is famous for the new element nihonium. Yeah, and very recently that facility is upgraded in terms of intensity and energy of a heavy ion linear accelerator, and we have installed also the new device to detect the new element, for instance, 1/19. Okay, so now that upgrade has been completed, and we are moving to the new element 119. So experimental group here is searching for that the new element. Okay, let me go to the new facility. Okay, at the new facility, we have a superconducting ring cyclotron that is a world world first and also strongest cyclotron in the world. And this cyclotron can deliver the fast primary beam. That the typical speed of that heavy ion beam is 70% of speed of light. Okay, and that beam is irradiated to the target. You can see that the target in my slide. Okay, yeah, and at the target that the primary beam, primary ions, okay, converted into the radioactive isotopes by reactions, okay, and radioactive isotopes are running at the speed of 60% of speed of light, yeah. So at the downstream of a target, we have an in-flight separator. So in-flight separator collect that radioactive isotopes as many as possible and separate that the isotope of interest. Then at the end of in-flight separator, so radioactive isotope beam delivered to the many several experimental areas. So that new facility started in 2007. At that time, for instance, uranium beam intensity was not so high, but our accelerator staff made the effort to increase the intensity of uranium beam by, for instance, a factor of 3,000. Yes, and year by year, yeah, and then accordingly that we have found that 152 new isotopes since 2007. Okay. So, so here I did list up the 4 research area in the nuclear physics. So maybe you are not so familiar with nuclear physics. I don't know, you got the credit of nuclear physics in student days, but let me introduce that the 4 topics and 4 subjects in the nuclear physics at the RIBF. So first one is that the shell evolution. So how that the shell would be changed as a function of proton numbers and the neutron numbers. Yes, that how, I mean, shell structure in the nucleus is very important to understand that the nucleus. Yes, and the second one is, as I said, that well, we like to know that the nuclear synthesis, how uranium is made, how gold is made in the universe. So we like to know that the nuclear properties of very neutron-rich nuclei, for instance, the mass and the half-life and etc. And the third one is neutron correlation. Well, it sounds difficult, but if you are familiar with the condensed matter physics, so in the condensed matter physics sense, that we like to have observed the BCS and the BEC crossover in the nuclear system. And the last one is equations of state in asymmetric nuclear matter. Asymmetric means that the pure neutral matter, okay? So equation of state, that is a stiffness of nuclear matter, okay? So that how stiff or soft of that nuclear matter is as a function of pressure and the temperature and so on. Such information is very important to understand that the supernova explosion and also structure of a neutron star. And if you like to analyze that the gravitational wave, you need that the equation of state information. Okay. So how to get such a new result? So here, well, I show that some example of that large international collaborations. Yes, I don't like to read one by one, but you can imagine that the European colleagues, US colleagues, Chinese, Korean colleagues bring their own detectors. Yes, and then form the large detector setup. Yes, to increase, enhance the efficiency of, for instance, gamma ray detection and so on. Yes, then, we have take data efficiently with many people. Yes, then we share the data. Then many people analyze the data and lots of publication. Okay, that is a typical style at the RIBF. So you can see that the number of users at the new facility. So year by year, that the number of users is increased. But unfortunately, because of COVID-19, almost number of users is decreased in 2020 and 2021. And so the significant fraction of users from EU. Okay, so 15 to 30% users from Europe. And we have many of MOU, and we have MOU-based EU partners. Okay, you can see that the flag. I don't read one by one, but you can catch up that we have a very thick connection with EU community. Okay. Okay, this is a very selected highlights at RIBF. So since 2007, many of publication, yes, many papers are published, and it's hard to choose it, but I just pick up the some of them. So concerning the shell evolution, so we found that the new majesty of n equals 34, neutron number 34 is a new magic. And also nickel 78, that is found to have a double magic nature. That means very stiff nucleus. And concerning the EOS, we found that we got some information of stiffness of neutron-rich nuclei, and we successfully measured that half-life of many of unknown neutron-rich nucleus. And concerning the neutron correlations, we found that the new halo neutron halo systems like neon magnesium 37, fluorine 29, and also we found that the di-neutron correlation in lithium 11. Okay. And not only basic science, but also we are very serious how to solve that the radioactive waste problem for sustainable world. So as you imagine that, so we can make the radioactive iso beam of long-lived nuclei in the nuclear waste. Okay, so since several years ago, we made that radioactive isotope beam of long-lived fission products at RIBF. Yes, and those by utilizing those beams, we did take that basic reaction data. Yeah, so and we got the data. Then after that, we asked that the Japanese Atomic Agency people to make a database. Yes, and according to the database, we made the simulation how to transmute long-lived fission products to the stable one or short-lived one. Yes, and we got some strategy how to transmute the long-lived fission products. So, well, we are now continuing. So those projects were supported by the impact project. And now that project was finished in 2018, but still we are investigating the how to make efficient transmutation for the long-lived fission products. Okay. So if you are interested in it, you can find my article in the Nuclear Physics News 31. Yes, that Nuclear Physics News is operated by NUPEC, European Nuclear Physics Community. Okay. And well, concerning the future, so we like to challenge that the three subjects. Okay, so well, we like to answer the question. So, can human beings freely recreate elements? Yes, we like to say yes, of course, and for that, yes. So we like to find the three pathways. First pathway is so how to reduce the radioactive waste, and the second pathway is well, we like to find out that the pathway of how uranium is created in the universe, and the third pathway is how to make an island of stability. Nuclear in the island of stability. Okay, so well, to conduct the three challenges, we need the more intense speed. So our accelerator staff is considering how to increase the beam intensity, and so they have a nice idea. Well. Of charge stripper rings, and that rings can enhance the beam intensity significantly. So now that the accelerator people designing that the new device, charge stripper ring, and we are requesting the budget. Okay. Oh yes. So. So let me show some video. Okay, so please visit our site for enjoy and learning. Okay, so you can find 8 contents, and one of them is a video of the facility tour. Okay, so that video is entitled that RIBF cruise. Yes, and that video has 11 minutes length. But today I showed that the short version, 3 minutes. But unfortunately, I have just 1.5 minutes. So, but anyway, please start at the video. Yes. Okay, so so that is entrance of our facility. So yes. So our facility is in the underground. Okay, so we are going to the area of cyclotron of SRC. So you can see that the world's heaviest cyclotron. Yes. So this cyclotron is weighted 8,000 tons. Yes, yes, SRC. So unfortunately, non-English version, but we are preparing that English version. So we are now going to the in-flight separator. Okay, so climb up, and. So you see that you can see that many tanks are there, right? So each tank has 3 quadrupole superconducting quadrupole magnets. Okay, so we are going to the downstream. Yes, downstream. Okay, so this is one of the experimental setup. That setup is called Samurai. Okay, so uh, uh, so that the blue one is a huge superconducting magnet to analyze the heavy ions. Okay, please stop that video. Okay, please stop that video. Okay, so time is limited. So okay. So you can visit the website, then you can enjoy the 11 minutes video, okay? Okay, this is my last slide. Well, I did give some specification, peak performance, major achievements, and how to access, and also useful links. Thank you very much.
Thank you very much for Dr. Sakurai for this comprehensive presentation and also contributing to keeping the time. Very much appreciated.